Morning, everyone. Mr. Benson and I are going to take this show on the road. If this works, we're going to Hollywood. Again, sorry if my voice is hard to understand. I got a cold. We have just finished integrating, and the one thing that we haven't talked about yet is what do you do with natural logs as well as with exponential function. So here we go. Our goal today is to do a differentiation, which sounds kind of weird because you might think, so why is she integrating? You probably noticed that I didn't ask you to do this integral before, and that was for good reason, because it would be x to the negative 1, and when you go to integrate it, you would get the following, which is kind of like bad news. The way they wiggle around this is to define the function that's going to stand for the antiderivative for this, and here's what it is. The natural log function is defined to be the area under a particular curve. And it's a familiar one, and they're only using the right side of it. They're taking the curve 1 over x, and they're having you start at 1. And here comes the 3 possibilities. Sorry about that. If you happen to integrate from 1 and you go to the right, I hope it makes sense that this area would be positive. So the integral of 1 over t dt from 1 to x would be a positive number. And since natural log of x is equivalent or equal to this, for x is greater than 1, the natural log of x would be positive. The one that's in the middle is you're going to integrate to a number between 0 and 1. And check this out. When you integrate from 1 possibly back to 1/2, you'd be going toward the left. So that means that that integral would be negative. And since this is just another way to write it, the natural log of some fraction between 0 and 1 is a negative number. And this one's my personal favorite. It's to take the natural log of 1, and what it has you do is integrate from 1 to 1, and nothing is there, so the area is 0. So likewise, the natural log of 1 is 0. The interesting thing is, you knew that from last year. Last year in pre-calc, you'd say the log of 1 base e is equal to what? And then by the broken arrow, e to the 0 is 1. So you already knew that the natural log of 1 was 0. The really cool part is you didn't know there was a whole world of geometry and graphing that went behind this. What I'm going to do now is take this information and try to put it together to sketch what y equals natural log of x looks like. This is probably the best way to start by saying the natural log of 1 is 0, and then here, as you move to the right and you want to take the natural log of numbers bigger than 1, those answers would be positive. So I'm just going to eyeball it like this. If you take and you want to integrate and you're going toward the left, like toward 1/2, 1/3, etc., those are all negative. So there's kind of a quick eyeball of what natural log looks like. And then over here I just tried to capture all the little pieces. Since you can't go to the left, the domain will be from 0 to infinity. The range is the whole enchilada. Mr. Benson said I should mention Chipotle now and then. So we're going from negative infinity to infinity. And these are just little hints. You can see that this is a continuous curve. It appears to be increasing, so that will be kind of interesting when we do the first derivative. And you also notice that it's concave down, and once again that'll be interesting when we do the second derivative. Now I added a little thing over here that says the curve is 1 to 1. From pre-calc you remember that it means that it passes both the horizontal and the vertical line test, and the beauty of that is if it passes both of them, you have a function whose inverse is also a function, and if this is y equals natural log of x, don't be surprised if later in this chapter, if this is 1, 0, this is 0, 1, like I said, don't be surprised if this guy shows up. and some of you probably recognize it as y equal e to the x. So that's a story for another day. What's going to be on this page, everybody, is we'll simply run through some properties of logarithms that will be helpful when we get to the derivatives and the exponent or the antiderivatives. These are from pre-calc. We just talked about this one. The natural log of 1, as you know, is 0. Mr. Benson, the natural log of a product is the...
I think the sum of the two, right?
Okay.
So natural log of A plus natural log of B.
And the log of a power.
Can't you bring this n down in front of the natural log, and it's n times natural log of A?
Done.
Oh, good.
And the log of a quotient.
Well, the quotient, if the product was addition, I would guess this one would be subtraction.
Got it. Okay. We'll use these properties. Mr. Benson, you want to do this first one for me?
Yeah, well, let's use the fourth property, and we'll change this to natural log of 8 minus natural log of 3.
That's good enough for me. Next one.
I'm not sure this. We got this square root here. Isn't that the same as to the 1/2 power?
Okay.
So can we bring that to the front, that 1/2, and do?
Okay. Obviously, you can think faster than I can write. Yep.
So 1/2 natural log of 2x minus 1.
Done.
Well, let's use. This is just kind of like the first one, but with an x in there. Let's call this natural log of 4x minus natural log of 7.
That's true. And then you've got a log of a product.
Oh, we got a log. Oh, yeah, we could expand. I didn't see that. So we could change this natural log of 4 times plus natural log of x minus natural log of 7.
Okay, looking good.
Why are you doing this to me, Mrs. Gowan?
Go for it.
Okay. Well, we could start off. We could say this is natural log of x squared plus 4 to the 3rd power minus natural log of x times the square root of x to the 3rd plus 1. Is that good so far?
I think so, because you've got the log of a quotient.
Okay. And then if we take this first one, the natural log of x squared plus 4 to the 3rd, we could change that to 3 times natural log of x squared plus 4.
Good.
Minus, and we could split that natural log of x and the square root into 2 by subtraction. So we could say natural log of x, through addition, sorry.
Yep.
Natural log of x plus natural log of, should we do it all in one step here?
Yep. I'm running short of
room.
room.
1/2. Let's change this 1/2 natural log of x to the 3rd plus 1. How does that look?
Good. Just be careful if you had to...
Oh yeah, the common mistake.
Yep.
Make sure you distribute that negative within there.
The things that Mr. Benson and I just did are practice for when we actually do a derivative. You'll find that if you can use these properties of logarithms, that the calculus part will be easier. The thing that's coming up next, the definition of E, I know that you're familiar with it, and it turns out that I'm going to give you a geometric or a graphical approach to it. Based on the front page, the natural log of E will be the area under the curve y equals 1 over t as we go from 1 to x, but we are defining it as it will be the number that will give us an area of 1. And continuing on, E is that number that makes the area under the curve equal to 1. So Mr. Benson, in case somebody doesn't have it memorized, you want to give them a hint. E is approximately how big?
It's approximately 2.718, 2.7-ish.
Sounds good. Now it turns out everyone is familiar with this from last year, because what you would do is, Mr. Benson, we called this log naturel. We pretended we had a European flair to it, because I think in French they say the noun and then they say the adjective next or something. So we make it Americanized and we call it log of E base E. So E to what power is E? We knew it was going to be 1. So probably everybody watching this wonderful video today is thinking they already knew that the natural log of E was 1. But it turns out, should we keep going? It turns out this expression is such that the area under the curve from 1 to Euler's number is such that the area would be equal to 1. If you're comfortable with the natural log of E equaling 1, you can use that to find natural log of e to other powers. For example, since the natural log of e to the third would be the same as 3 times the natural log of e, and since we just got through saying the natural log of e is 1, there's a handy little hint for simplification in the future. We are getting closer and closer to the calc. Okay. It turns out what we are headed for, everybody, is we'd like to be able to take the derivative of the natural log function. And from the first page, this was our definition. It said that natural log will be defined to be the area under this curve from 1 to x. And I know that many of you thought the second fundamental theorem of calculus was a bit of a joke.
No.
Well, but now you'll actually see our use for it. So this is it, guys. If two functions are equal, then their derivatives will be equal. So I'm going to take the derivative of the left side and the derivative of the right side. Check this out. The derivative of the antiderivative of a function starting at a constant going to a variable, the second fundamental theorem of calculus says that it's going to be a wash. They're going to undo each other, and my friends, all you're going to have is just 1 over x.
So really you just take this x in the integral and you plug it in for that t?
That's exactly what you do. So here's the story, guys. When you take the derivative of the natural log of x with respect to x, your answer is 1 over x. And please keep in mind that we never go into the second and third quadrants. We keep everything on the right side of the graph. And Mr. Benson wants to tell you when the world gets complicated and maybe you have a function of another function. So take it away, Mr. B.
So in certain situations, if I'm understanding this correctly, if u, say, were to be x squared, we got to use the chain rule in this situation. So if we let u be x squared and using the chain rule, I would find the derivative of the outside, which would be 1 over u, which we know is really this x squared in disguise, and then we multiply by the derivative of u, which is really x squared, and we all know that the derivative of x squared is 2x. So in this situation, this hypothetical situation I made up, I would combine these two together and get 1 over x squared times 2x. With a little bit of simplification, this gets me 2 over x. And that's kind of the gist of what this little theorem is talking about, using the chain rule to solve these things.
Yep, exactly. So all we have left, everybody, is just a smattering of derivatives to take. This is kind of like a 2-day type of deal. For Monday, we'll kind of practice taking the derivative of natural log, and then we'll spice it up a little bit on Tuesday with, as you can imagine, tangent line, slope at a point, horizontal tangents, and all that good stuff. So I'm going to draw a little box around these. That's not a mathematical term. Actually, it's called the argument, and I'm going to hand this pen over, and Mr. Benson is going to take it from here.
What are we going to do with these boxes? Why are we drawing boxes?
Because I'm thinking that will help the students remember that it's 1 over the box.
Oh, yeah, that's a good point. And then we would take the derivative of what was in the box.
Yep.
So if I were to rewrite this, I know the derivative of natural log of box is 1 over box.
Yep.
So let's see, we got, no. I don't know how to use this board as well as you. Here we go. So we got 1 over box.
Yep.
Times, do you write it like this, derivative of box?
You can.
With respect to u?
Do it that way and you get, well, with respect to x.
Oh, with respect to x, of course.
Okay.
And so this is equal, well,
unfortunately, we have to go back and see what was in the box.
What was in the box, yeah.
Very cool.
So we got 5x. So
yep.
This is equal to 1 over 5x. And then the derivative of the box, which was this one, is equal to 5. So we multiply by 5.
Yep.
And so this is going to be 5 over 5x, which is the same as 1 over x. Did I do that wrong?
Done? Nope. Isn't that weird?
Oh, it just goes away.
Oh, yeah.
Oh, weird.
There you go.
Oh,
that's the derivative.
Oh, wait, you got to box it. Okay. Okay, so let's do this one. We're not going to do all the boxes in this situation. We're just going to try to skip that.
Think about it.
We'll think about it a little bit here. So we're going to have 1 over x to the third minus 1, and we're going to multiply the derivative of the inside of this box right here, and we get 3x squared. So our final solution would be 3x squared over x to the third minus 1.
Yep.
And box it.
Well done.
Thank you.
And
Ooh.
big excitement.
Okay, this is kind of flipping it. Okay, so this is the most outside part of the function of this composite function, and this is the next part, and that's the most inner part. So let's take the derivative of this outside. So we're going to get 3 times the natural log of x. And the derivative of the inside natural log of x is 1 over x. And this would simplify to be 3 natural log of x over x. Is that right?
Nope.
Oh,
I think you've got a power.
I forgot the power. Oh, embarrassing.
Only minor.
Yeah. very
Okay.
minor, but still
Looking
wrong.
good.
Oh, forgot to box it. Guys,
Okay.
can you see this? This is a square up there, in case you can't see that.
Very good.
Okay. And then we got one more.
Little drum roll for our last one.
Okay. I'm a little nervous after that last one right there. So here we got natural log of the square root of x plus 1. So we want to find the derivative here. So it would be 1 over the square root of x plus 1. And now we have to find the derivative of the square root of x plus 1. Isn't that 1/2 x plus 1 to the negative 1/2? And we can simplify this more. How do I expand this page?
I think that I'm going to put you in your
Oh
place.
my gosh, what did I do wrong?
Nothing, but this is like Wonder Woman to save the day. Ta-da. We did this on purpose, guys. Why don't we write this as 1/2 the log? Because the log of a power is a power times the log.
I did not see that.
I don't
Right.
know.
We're gonna
So
be-
not even there. How about if we go there?
Okay, so we're going to take this is 1/2 natural log of
Just
plus 1.
perfect.
Okay,
Now we're going to do the derivative.
and now we can do the derivative of that. Oh, this is going to be so much easier. So this, the derivative of this would be 1/2. We still have that 1/2
Yep,
here.
yep.
Of 1 over x plus 1. And then multiplied by 1, because the derivative of the inside right here is 1, so we don't really have to do anything. Let's just make this a nice, good 2x plus 1.
And as we say, the party's over.
Party's over.
The sound you hear is a high five.